Okay, question number 1a. If fx equals to set x plus 1, x greater equals to negative 1, find f inverse x. So to find f inverse x, we will use f inverse x is equals to x. That means, okay, from this function fx, we will change x, wherever we have x, we will change it to f inverse. So f inverse is equals to set f inverse x plus 1. So f inverse equals to 1, so set f inverse x plus 1 equals to x. Okay, so rearranging our equation, f inverse x plus 1 is equals to x square. F inverse x is equals to x square minus 1. And since we have our fx is, we have fx, we have x greater equals to negative 1. So for f inverse, we will have x greater equals to 0. Okay, so that's it for question 1a. 1a1. Question 2. Sketch the graph of fx and f inverse on the same axis. State the domain and range for both. So we have fx is equals to set x plus 1 for x greater equals to negative 1, and for f inverse we have x square minus 1 for x greater equals to 0. So we will sketch both graph on the same axis. Okay, so draw the axis first. This is x, this is y. Okay, I will just orange for fx. So set, this is the shape of set, and to draw set, okay, this is the basic shape of set. Then we have inside the set x plus 1. So the starting point of this set, okay, this starting point, okay, so x plus 1 equals to 0, x equals to negative 1. So this is our negative 1 and our set. So this is our fx. Then for our f inverse, I will use green, x square minus 1. So this is x square minus 1. Okay, and our minimum point here, k. So, and we have the interval x greater equals to 0. So this one is our f inverse. Okay, and when we draw fx and f inverse, okay, please draw also a dotted line, a dashed line, y equals to x. Okay, to show that fx is reflected at y equals to x to be f inverse. Okay, so the orange is fx, the green one is the f inverse. Okay, so now the domain and range for both. So here we use relationship between fx and f inverse. Domain f is equals to range f inverse. Okay, and to find domain f, domain, we will look at the value of x. So okay, look at the orange graph. Okay, the value of x starts from negative 1 until infinity. Okay, so negative 1, infinity, and the negative 1 is included. Okay, and we can also look from here. This is our interval actually. Sorry, this is our domain for fx. Okay, then we want to find range for f. Range f is equals to domain f inverse. So to find domain f inverse, we can also look from here. Okay, and from the graph, we can also see that, okay, the value of x start from 0 until infinity. So range f or domain f inverse is equals to 0, infinity. Okay, dah siap. Okay, question 1b, given fx equals to ax plus 2 over 4x minus 3, where x now equals to 3 over 4. If f1 equals to 1, find the values of a. So from this question, we have fx is equals to ax plus 2 over 4x minus 3. And we also have f, so the composite of ff, and we substitute x equals to 1, so we'll get the answer is 1. Okay, so now first we will write ff, composite of ff, like this. Okay, I think this is easier lah. Sorry, f1 equals to 1. So to make things easier, first we need to find what is f1, then we substitute the value of f1 into our f. Okay, so now f1, okay, just substitute x equals to 1, so a times 1 plus 2 over 4 times 1 minus 3, so f1 is equals to a plus 2. So we will substitute this f1 equals to a plus 2 into f, okay, because f1 is equals to a plus 2. So in our fx, wherever we have x, we will substitute it with a plus 2. So a plus 2 over 4 a plus 2 minus 3, and this is all equals to 1. Okay, so we just calculate this 1, so a square plus 2a plus 2 over 4a plus 8 minus 3 equals to 1. A square plus 2a plus 2 is equals to 4a plus 5. A square minus 2a minus 3 is equals to 0. So we have a quadratic. So just factorize the quadratic. We'll get a minus 3, a plus 1 equals to 0. So a minus 3 equals to 0, a equals to 3, and a plus 1 equals to 0, a equals to negative 1. So the values are a equals to 3 and a equals to negative 1. Okay, question number 2. Find the inverse function of fx equals to e to the power of x plus 1 minus 2. Determine the domain and range for f inverse. So we have fx, we need to find the domain and range of f inverse. So obviously we need to find f inverse first. We will use f inverse x equals to x. So from fx equals to e, x plus 1 minus 2, we will change our x into f inverse. Okay, so our f inverse x is equals to e f inverse x plus 1 minus 2, and the whole thing here is equals to x. Okay, so e f inverse, now we are going to rearrange it. Okay, equals to x plus 2, then ln both sides, ln e f inverse x plus 1 is equals to ln x plus 2 f inverse x plus 1 is equals to ln x plus 2, then f inverse x is equals to ln x plus 2 minus 1. Okay, now we need to find what is domain and range for f inverse. So the domain of f inverse, okay, just remember domain is the value of x. So to find the domain of ln, we just need to look at the thing in this bracket. Okay, so first we need to remember for ln, okay, for logarithmic function, for ln, the value inside the bracket must be greater than 0, because we cannot have ln 0, we cannot have ln negative. So inside the bracket we have x plus 2 must be greater than 0. Okay, this is the important thing here, greater than 0. The thing inside bracket only. Okay, then okay, just rearrange. So x greater equals to negative 2. So this is our domain. Okay, then we need we write it first. Domain is negative to infinity. And now we will look at the range of f inverse for ln. The range is, okay, the range is always negative infinity to infinity, except if we have other condition. For example, the question stated that fx has interval between something, so range cannot be negative infinity to infinity. But if we have like this question, fx, you just give fx and we don't have any interval, so the range of ln will always be negative infinity to infinity. Okay, then if you look at the graph, okay, even though the question didn't ask to sketch the graph, okay, just show. So we have ln, so from ln we have vertical asymptote at x equals to negative 2. Okay, so this is actually will give us the asymptote. Okay, so x equals to negative 2. Then we have ln x plus 2, so the graph is going to be like this lah. Okay, so this is our f inverse x. Okay, and as you can see from the graph, okay, x, y, the domain is negative 2 to infinity. Okay, then the range is negative infinity to infinity. Okay, that's it. Okay, now we will look at example for limits and continuity. Okay, question number 1, sketch the graph of fx. Okay, so as we look at the question, fx, we have a piecewise function which includes negative x minus 3, which is a linear graph, fx equals to negative 3, okay, a constant graph, and fx equals to ln x plus 1, graph log. Okay, and from fx determine, okay, and hence determine its continuity at x equals to 0. So first we need to sketch the graph. Okay, as we said just now, negative x minus x is a linear graph. Okay, so linear graph with negative gradients, so the basic shape is going to be like this. Okay, then fx equals to negative 3 at x equals to 0, so it's going to be a dot, just a dot, and fx equals to ln x plus 1, so we have ln positive, so it's going to be like this. Okay, so that is our basic shape of our piecewise function. Then, okay, now we're going to sketch the graph. Okay, so this is x, this is y. First, we're going to look at fx equals to negative x minus 3. Okay, that we have interval x less than 0. So to make things easier, Okay, we just let when x equals to 0, so we'll get fx equals to -3. Okay, just substitute x equals to 0, then fx will get -3. Then when fx equals to 0, we'll get x equals to -3 also. So from these two calculation, we'll get two coordinates, 0, -3, and -3, 0. And remember, -x, -3 is a linear function with negative gradient. Okay, so we're going to plot the graph x0, fx -3, or y equals to -3. Okay, I will change the axis first. Okay, so x0, fx equals to -3. Okay, so this one, oh sorry, I will use different color. Okay, now we're missing the axis. Okay, so x0, fx -3 is somewhere here, and x equals to -3, fx equals to 0, so maybe somewhere here. Okay, and this is a linear, so we just connect these two dots. Okay, then just draw a straight line. Okay, but as we can see here, we have x less than 0. That means, okay, this is an empty circle. Oh, we're missing the lines again. Okay, again. Okay, and x equals to 0 somewhere here. This one, I'm so sorry. So again, okay, I think this one. Okay. Okay. And okay. Here, empty circle. Okay, now we're going to look at the second function, fx equals to f0 is equals to -3. So exactly at x equals to 0, fx equals to -3. So here is -3. Okay, -3. Yeah, okay, this one is also -3. Okay, now look at the third function, fx equals to ln x plus 1 for x greater than 0. Okay, so first we look at the asymptote. Asymptote here we have x plus 1. Okay, x plus 1 greater than 0, x greater than -1. This is our asymptote, but then our ln is from x greater equals to 0. So we will just ignore this asymptote. So now easier way is just substitute x equals to 0, then we'll get ln 0 plus 1 ln 1, so ln 1 is equals to 0. So that means our third graph will start at the origin 0, 0 here, and just draw the ln graph. Okay, so to sketch the piecewise graph, look at the function given one by one, and it will be easier if you just sketch the basic shape besides the function and then look carefully at the interval. Okay, maybe it will be easier if you just substitute the value given from the interval. Okay, so this is our graph. Okay, so next, determine the continuity at x equals to 0. So as we can see from the graph is not continuous at x equals to 0. Okay, because the graph is not continuous. I mean, the graph is not connected at x equals to 0. Here we have -3, and then here we have 0. So we're not connected. Then we just need to prove by the 3 condition. Okay, so we can see that from the graph fx is not continuous at x equals to 0. So you can just state the first condition. The first condition, we have f0. So f0 is equals to, okay, from the graph f0 equals to -3. Then we look at the second condition of continuity. Okay, we are now discussing on the conditions of the continuity at x equals to 0. So the second condition is the limit x approaching 0 fx exists. So as you can see from the graph, the limit does not exist. So we just prove it. Limit x approaching 0 from left. Okay, 0 from left, the function is -x minus 3. -x minus 3. So the value is 0 minus 3. Then we get -3. Okay, now limit x approaching 0 from right, the function is ln x plus 1. So just substitute x equals to 0, we'll get ln 1. So ln n is equals to 0. And since limit x approaching 0 from left is not equals to limit x approaching 0 from right, therefore limit x approaching 0 fx does not exist. Hence we can conclude that hence fx is not continuous at x equals to 0. Okay, so we're done.